Hello and welcome to episode 4. It is 3:08 in the morning and I cannot sleep. That's not true. I could sleep if I wanted to, but I want to get this take. This is going to be take 2 because I just freaking wrote all this code, and then when I went to record my desktop, I accidentally hit Windows C, which is my macro for closing the terminal, instead of Control C, which is what I was supposed to do. But good news is I'll hopefully make less mistakes because I just did this. But it's also 3 in the morning, so, we'll see. Anyways, I don't actually have the PDF up right now, but you can check it out. We've moved on to step 2 of the FASTA algorithm, which is scoring the diagonals. So I've beefed up this little picture here, and here is basically our dot plot with a k equals 1. Which means that each and every one tuple, or each and every character that matches its corresponding character in the other string, gets a 1. Okay, so the diagonals represent matches of that length. So you can see that these 5 characters, A, T, C, G, T, on the left string, string 1, match A, T, C, G, T here. And then there's a mismatch. A does not match T, and then another length 3 match. So the longer the diagonals, the better a local alignment is. And that's why we are trying to score these things. And so I've put the scores of the diagonals down here and up and over here, and I'll just show you how I got these. 8, this number corresponds to this diagonal, and there are 1, 2, 3, 4, 5, 6, 7, 8 matches. Okay. And so we can enumerate the diagonals. Let's say this main diagonal is diagonal 0. No, let's say it's diagonal 1. So there are m diagonals across the top, and then there are n diagonals across the side. And so the total number of diagonals is m plus n, but then you don't want to double count the main diagonal, so minus 1. So that's how many diagonals there are. So if I were to make something like a list, where each index corresponds to a diagonal, the list's size would be m plus n minus 1. Okay, so that's all fabulous. Let's start coding. Oh god, it's so late, and I'm so tired. Okay, so first, before I forget, this is a mistake I made last time. I'm going to set k equals 1, just so we can match up my numbers here to the numbers that this thing's going to eventually spit out. Okay, and another thing I have to do preliminarily is I was getting a non-exhaustive pattern match in this function here because I forgot to account for the case where k could be 1, so we'll just fix this like so. And sorry I'm moving through this pretty quick, but this part doesn't really matter, just little tune-ups. So here's where we get into the interesting code. So first I want to be able to map an ij location cell to which diagonal it's on. And so I'm just going to arbitrarily decide that this bottom left corner is diagonal 0, and then this would be diagonal 1. Oops, sorry. This diagonal right here is diagonal 1. This diagonal is diagonal 2, and so on. So this corner diagonal would be diagonal n minus 1, and I'm going to switch these around just so I can be consistent. Where the left string is string 1 of length n, and the top string is string 2 of length m. So this is diagonal n minus 1, and then we continue on until we arrive at diagonal n minus 1 plus m minus 1. 2 minus 1s. I think I got that right. Okay, so let's make a function diag_index, and it's going to take a cell and tell me what diagonal it's on, but we need that extra bit of information, which is n, because remember, we don't really care how long m is, but we for the purpose of indexing, but we do care how long n is because when we so remember that this main diagonal is where I minus j equals 0, or j minus I equals 0. Here, j minus I is going to be -1, right? Because j is 0 and I is 1. So down here, j minus I is going to be -n. And so for that reason, I need to add, or so it's going to be -n minus 1. And so I need to add back n minus 1 so that this becomes index 0. Sorry if that wasn't clear. I don't know if that explanation made any sense, but basically we just have to add an extra parameter here. So kind of what I was just saying, we have to add back n minus 1 to make sure that this is diagonal 0 and not diagonal -n minus 1. Okay, so now we're going to start writing the main diagonal scores function. And it's going to take in a dot plot and return me a bunch of diagonal scores. And I think I'm going to do something similar to the index map function here, because just thinking about it, what I'm going to be doing is iterating over this map, and for each value in the map, which is going to be a list of integers, sorry, a list of tuples, I'm going to convert each tuple to its diagonal index, and then I'm going to increment that index in this big list of ints. So this list of ints is sort of my state. So I'm going to basically do exactly this little pattern that I came up with earlier. And my inner function is going to be in the state monad. And its state is going to be a list of ints. Okay, so what this function needs is the dot plot. Sorry. The initial state is going to be, like we talked about before, an array of n plus m minus 1 zeros. And so I need 2 extra parameters. And I'm going to use the replicate function. Make sure I have these in the right order. 2, 3 makes 2 3s, so well, I'm going to do this. Okay, so let me just make sure, yeah, I got that right. Okay. Okay, so how is diagonal scores tick gonna work? So I think for now what I'm going to do is make it easier on myself for the time being, and instead of passing in the map, I'm going to pass in a list version of that map. So let's call this x's. And what x's is a list of tuples, key value pairs where the key is a string and the value is a list of int tuples. So that's the type of x's. So what I want to do is map over x's basically an action in the state monad. And what I want to map over x's is, first I want to get the second. And after I get the second, then I have the list of int tuples. Then I want to get the diagonal indexes, or basically convert that list into a bunch of dag indexes. So now I have a list of ints. And then I want to do an action in the state monad, which is going to be called increment dags. And this is going to be over x's, so this function can be reduced. Okay, so each increment dag is going to receive one list of dag indexes, and what it's going to do is, if it receives an int and a list like 1, 2, 2, then it's going to have to get the state, and then with that state, and these all are not going to be, well, they're going to be 0 the first time. It's going to increment the appropriate indexes the appropriate number of times. So how I'm going to accomplish this is with a library called Lens, and Lens is super fucking amazing, and it does lots of shit, and there are three core concepts to learn and use and know about, and that would be lenses, folds, and traversals. And you could spend your entire fucking life reading through the documentation of this library. It's huge. It's just it's control.lens, capital L, or sorry, lowercase l, lens is the library name. So I'm going to show you how to do specifically this with the lens library. And I'm going to use a function called element, which takes a number, an integer, and then I'm going to set the value at that index to say 1, and this entire thing is going to be on, say, this list. Let me do that one more time. Okay, so we can see that I have set element number 2 to 1. And there's a little bit nicer syntax that uses ampersand, which is basically just a flipped $sign. It looks like this. And if I give it an index that is basically out of range, essentially nothing happens. And let's go back to modifying element 2. So I can also, that just sets it, I can modify it with the function. And the state equivalent inside a state monad would be %equals. That is the operator that I'm going to use. So I know that was a very, very brief and horrible description of, or introduction to the Lens library, but fuck, it's 3:20 in the morning, and it's actually a really awesome library, and I highly recommend poking around because you can do a lot of stuff with it. But this is a very simple use case. So basically I have an x's again, and what I want to do is another map. I don't care about the return value. And the function I'm going to use is, well, basically I have an index, and I want to set that index, or modify it rather, by adding 1 to it. So don't need this as an argument. And it doesn't compile. Oh no, that's because I forgot the import. Oops. Okay, and it's still not compiling. No. Oh god, what's going on here? So I forgot to change the type signature. This is going to look like shit. What is this? Okay. No? Not quite. Oh, sorry. I forgot that one. Okay. And finally, what's going on here? It looks like I forgot a parameter, which, okay, diag index needs to know how big string 1 is, so diag index n. And it compiled, which is a really good sign. So let's check this out. Oops. So, oops, let me get out of here. I'm just going to try it on these strings. ATCG. Sorry. TATCG. CAGAT. CGTCT. CGAT. And with my dot plot, I'm going to call diagonal scores. And hopefully these numbers will coincide with the ones I did by hand, which are, remember that this is diagonal 0, 1, and so on. So 0, 1, 1, 0, 1, 0. And it looks like it checked out. So yay! Okay, so thank you for watching. And next time, I think what I'm going to do is clean this code up a little bit because, oops, where is my, there it is. I realize now that I probably want to do an association list again because when k is 1, sure, this is all nice and dense, and I don't really gain much by not having any values, which is why I just use an entire array for all diagonals. But it may be the case that when k is sufficiently large, like if k is 11, then it's not the case that there will be every permutation of 11, or every index will match some other index in the database string. So this may actually be a sparse matrix. So for that reason, I think I'm just going to rip this code apart and kind of change the signature, but it'll end up being basically the same. So that is something to look forward to. And alright, 3:26 in the morning, hooray. Yeah, thanks so much for watching. See you next time. Control C, Control C, Control C.